an plus 1 equals an minus f of an. Furthermore, suppose we can assume that f of an grows kind of slowly. So what can we do this equation with? Not a lot, because this is kind of implicitly assuming that this is like a continuous function, but this is like a discrete thing, this sequence. Let's be stupid to ignore that. Let's say instead it's let's suppose we could just do that. And let's suppose this sequence was a continuous thing that we could associate with some function a of n. Okay. Now this kind of looks a little like the difference quotient, right? It's kind of like the derivative of the sequence. So why don't we go ahead and say, just be really stupid, a prime of n equals negative f of a. Well, now this is pretty easy. So in this case, we would have j is equal to, sorry, j prime is equal to 6j 1/3. And I guess this is like or whatever. Okay. And so this is a differential equation that we just solve. And again, it doesn't have any meaning, right? Because it's discrete. But let's say we can say some reasonable thing about what it means to take the derivative of the number of joints. So with that being said, how do we solve this equation? I think it's been a bit since calculus for people. But,
Separations.
Yeah. I think. Okay. Shoot. What am I taking the derivative with respect to? N. Why do we do this? I genuinely don't know. Let's say, here, this will make it more easy for me to understand. Let's say y prime equals, there's something familiar about that. 6y 1/3. Okay, so now it's easy. So dy over dx equals 6y 1/3. So dy over 6y 1/3 equals dx integrates. Go from here to here, sure. X equals
Times.
Is it 3/2 times that?
3/2 times then the deal 1/6.
Cool. 3/2 times 6y 2/3
Times 1/6.
Where's 1/6?
Is the 6y
Yeah. Okay.
plus c.
I'll say that because we can make no joints when we have no lines, we'll ignore the plus c. I think that's reasonable. Okay.
Actually, where does the C go then?
Don't worry about it. So I think it was joints as a function of lines, so we'll translate back. Number of lines is 3/2 times 1/6 is something north. I can't tell. Whatever. I'm going to go with it, and I think I made a arithmetic mistake, but just buy it for now. 4L over 6 to the 2/3, all to the 3/2 should theoretically equal J. See, that doesn't look right. Because that would get me 8 over 6. No, this is right. All right, cool. Okay, 4L, this simplifies to, I think, just 4/3, right? Because this becomes 8 and that becomes 6. Okay, so J is 4/3 L to 3/2. So theoretically, at least, that's better than what we had before. What was it? I think it's on this board? No, it's not. But I think before we had j over L is less than, like j over square root of 6? Yeah, j over square root of 6 is less than L 3 halves. And so 4/3 is less than square root of 6, and we beat that. So the question is why? And like, how does it make sense to take the derivative of the number of joints? So that's kind of the idea of this new improvement, is that if you have some sequence like this, then it is rigorous to approximate. And I'll kind of give you the intuitive reason why. That would be that it's because we know that f is polynomial. And so there's a certain sense in which this difference quotient thing makes a lot of sense. And that's this sense, asymptotically, which is what we care about. Okay, so what's this limit for polynomial function f? Okay, so I'll just do it for, and the proof's not more involved for other things, because polynomials are linear. So I think if I prove it, if I find out what it is for a function of the form like x to the k, or n to the k, it should become clear. If I have n plus 1 to the k minus n to the k over the derivative is like k to the k minus 1? Yeah, so then this, the first thing, the binomial gets gone, but then the second one is k times n to the k minus 1. So you get 1. And that's why it works.
Too small.
Right, because it's really the same. So if you make it rigorous, you can say that the joints is like squeezed between two polynomials that both grow at about the same asymptotic rate. And so it's rigorous to make this kind of approximation. So cool. Problem is, there's still an issue, because I think I claimed that this was our best lower bound. And so our upper bound is like, what do we have so far? Oh, lower bound.
Oh, look.
Yeah.
The upper bound.
Upper bound is 4/3. Okay. There's a difference. This is like 1.3. This is, I don't know. It's less than 0.5. There's a bit of a difference. So, interesting observation. What happens if you make this L over 2? If you plug in L over 2 to this side? Yeah, it's the same. And that actually, and I won't go into the computations here because I'm not going to have the time. It's not worth taking the time to do. But if you do the same argument, you can imagine that this works just as well in k dimensions as in 3 dimensions. This whole like finding the polynomial that vanishes, and that this solving the differential equation nonsense. If you do this all through in n dimensions, and then you get an upper bound and a lower bound. And if you plug in L over k minus 1, it always works out. It's always equal. And so that's very interesting. And so I think that motivates a conjecture. So the conjecture is that we can plug L over 2 in here, and it works. And so the way this manifests itself in the proof is that when we had this, the way we do this induction is we have a sequence of lines being removed. And so what the conjecture says is basically we can stop halfway through. So
the true value is the lower bound.
what?
So the lower bound is the true value.
Yeah, lower bound is
Contextually.
Yeah. Yeah, we conjecture that that's optimal. I guess I never. Yeah, I went over the planes of general position thing. Right? Yeah, we conjecture that's the best way to do it. And I guess that's a little different than saying that the lower bound is the same, but it's close enough that if we can prove that the lower bound is the same, then the configurations have to be the same. Okay. So the conjecture. This is really hard to state precisely, so I'll just do an example. If we have a cube, if we have a cube, then we take away this line that has 2 points, two joints on it, and then these joints are next out. Now we can take away this line which has 2 points. Now 2 is less than, okay? So this means we're allowed to remove it by our lemma. Because it's less than 6 times the number of joints L to the 1/3. Because this is where it would come in the proof because we're removing lines. Okay, now we can remove another one. 2 is less than, I'm pretty sure. So we can just remove another line that contains 2 joints. Sorry about this one. And we'll get rid of these. Now we have 4 joints left. And 1 is less than like 6 times 4 to the 1/3, 6 times 3, 6 times 2, 6 times 1. So basically if we remove 2 lines containing 2 joints each, and then like this line, this line, this line, this line. We removed all the joints. We've only taken half the lines to do it. And so the conjecture it says, the conjecture that's so hard to say precisely, is that no matter how complicated the configuration, you can find some subset of half the lines, such that each of the lines you're removing doesn't contain more than 6 times the number of joints to the 1/3. When we're done removing half the lines, there's no joints left. Okay, seems legit. Now we have a math question, how to generalize. So I already, I'll state without proof that you can do this very easily for k dimensions. So lines are not interesting. What are interesting? Planes are interesting. Those are fun. So where does this proof break down for planes? Anyone have any ideas? So let's do the steps.
You might want them to have a complementary dimension or something. So in general position, the intersection.
Oh yes, so you have to do it in 6 dimensions, because you want it to span each of the planes has 2 tangent vectors, and you have 3 planes, so you want it to be 6 dimensions. Okay, was that what you were asking? I think mine was something different.
No, it's just, well, something along the lines of that.
Well, if it comes up again, let me know. The proof works. We can definitely take a polynomial to vanish on all the planes, right? That's like fine. We can take a polynomial to vanish on all the points. However, the next step fails because there's no equivalent to saying that a polynomial that vanishes along a line must be 0. That's not true for a plane, because consider like the polynomial.
You use like Ferris polynomial?
Like this polynomial is like the 0 set is this sphere, which intersects this plane in a whole bunch of places, like a whole circle, which is infinity, but it's only degree 2, so it completely breaks. So the thought is to try to repair this. Something I worked on is, and I'll demonstrate it. I'm not going to have time to go through the whole argument, but basically I found a different proof for the one-dimensional, the lines in 3 dimensions that proof. I found a different way to do it than this that might extend more easily. And so I'll demonstrate it by doing the 2-dimensional version. So we're going to prove this theorem. It's going to be really deep. If we have P planes and L lines in R3, then the number of plane line intersections is at most P times L. Okay, I know. Okay. Intersections I is less than P times L. Obvious. So we're going to use this to prove something we already proved by obviousness, which was that if we have a bunch of lines here in the plane, then what do we say, n choose 2? Yeah, we're going to prove that. So n choose 2 is n squared over 2, so don't even worry about it. We're going to take half of these lines and push them into the 3rd dimension. So just give them an extra tangent vector, make them planes. Okay? So, and this is like probabilistic method stuff. So, we're going to turn them into P planes and L lines, where P plus L is n, which is the number of lines we started with. Okay, so on average, how many of these intersections fall into each category? So some of the intersections are going to be old planes times old lines. Old. Okay, so better way to do this. 4 mutually intersecting lines, whatever. So let's take this line and this line to become planes. And this line can remain lines. So on average, a quarter of the intersections will now be into 4 equally likely groups. So a quarter of them are going to be line-line intersections. Okay? A quarter of them are going to be plane-plane intersections. And then half of them are going to be either plane-line or line-plane intersections. And so that means that the number of intersections over 2 is less than the number of planes times the number of lines, right? Okay. And so a probabilistic method will make these both about n over 2. So that means I over 2 is less than like n squared over 4. So we've recovered this theorem. So the idea here is that we project our problem into the higher dimension and we get something a little easier. And then we project down and recover a divergent result. So I won't go into specifics, but basically, I will cite the theorem. Let me find this thing. It's really nasty. It's not that nasty. Okay. So suppose that L is a set of lines in 3 dimensions that intersect L to the 3/2 plus epsilon times. So L is a set of lines that contains, I guess, O lines and this many intersections. And this is, by the way, another polynomial vector theorem, but the proof is like 3 pages. It's really scary, so I didn't look at it. Then there exists a plane. Then basically you can take a plane that has that's a subset of these lines that all lie in a common plane that contains L to the 1/2 plus epsilon of the intersections. And it's either a plane or a regulus. So skipping a few steps here because I'm basically out of time. You can use this to prove the following 4-dimensional theorem, which is that if you define a joint as the intersection of 2 lines in a plane, then there must be at most like number of lines times number of planes to the 3/2, or something isomorphic to what we've said in the 3rd dimension. I believe it's that actually. You can prove that. This should be checked. And then what we can do is we can project some things down to R3 and recover this thing. So basically, this is a new way to do it because it doesn't run into that same snag that we ran into earlier, where you can just have a polynomial that just vanishes wherever it feels like on a plane, so that you can't do anything about it. Okay, so I guess it's kind of an introduction to the joints problem. So thanks.